Okay, so in this part of the lecture, what we'd like to do is see this connection between online learning and query release and start to analyze what we can do with that. So remember, our goal is we want to design an algorithm that takes as input a data set and produces a distribution, p hat, such that this maximum inner product of p hat minus h with the different phi's is upper bounded. All right, so here's the idea. We're going to design M as an interaction between two parties. Okay. And on one hand, there's going to be an analyst. And the analyst is going to propose a sequence of candidate synthetic data distributions. Okay, P1, P2, up to PT. So these will be these will be distributions over the space of possible data records. So we're going to imagine we've got this interaction. Over here, we've got the analyst. And so the analyst will propose, sorry, I want analyst to be bigger than that. Okay, the analyst will propose P1. And on the other hand, there's going to be a differentially private interface that will actually be the thing that's holding the data. And so here it will, okay. And what it's going to do internally is every time the analyst proposes a data set, this interface is going to go to the data and check how well the analyst is doing and try to find a query that exhibits just how badly the analyst is doing. So the interface is actually going to try to, so it's going to actually run T executions of the exponential mechanism. So it will actually be differentially private. And so the input to each of these executions, so that we're going to call the algorithm it runs called the internal algorithm like M naught. Okay, and its goal is to find a bad query. So it wants to find phi I such that, or it wants to find rather I, such that phi I times the current, phi I kind of roughly exhibits the current error of the analyst's distribution P sub T. So its goal is to find an I such the inner product of phi I and PT minus H is about the analyst's, about the as large as it possibly could be. All right, and so it's going to take as input this algorithm, M naught will take as inputs the data set X, a privacy parameter epsilon naught, and then this distribution P sub T. Okay, and there's no privacy. We're not concerned about privacy for P sub T. And it's going to output it's going to sample I sub T from proportional to e to the minus, e to the epsilon n times the score, epsilon naught n times the score of I and X. So this is the probability with which it's outputting. So give ourselves a little more space to write that. So the probability that M naught outputs I should be proportional to this score. And here the score I comma X is just how well phi I does at telling apart P hat from H of X. Okay, so actually a good mental model to think about is that what phi I is doing, what each of these phi's is doing is sort of trying to distinguish random samples from P from random samples from H. Okay, so what the interface is going to do, it gets this P1, it's going to run M naught with input P1 and X, and it's going to send back an index I1. And then again, it'll get another a candidate distribution P2. It'll run M naught and send back I2, and so on and so forth. So, and then in the last interaction, it'll send back I sub t. So it's going to run t copies of this exponential mechanism, each with some privacy parameter epsilon zip not. And our ultimate privacy guarantee is just going to be obtained by composing the guarantees for the pieces. Okay. So that's going to be what the interface does. So it's going to try to find a phi that exhibits that has roughly this maximum error. And so I want you to notice a couple of things about the score function here. Observe that, the error of P hat is indeed the maximum value of the score function. So running the exponential mechanism is a reasonable way to try to get your hands on an index I that has roughly maximal score. And just to check that we're setting things up properly, the sensitivity of the score. Well, if data sets X and Y are neighbors, then for any given index I, so recall the sensitivity of the score function is for each of the possible outputs I want the score of I to not change very much. So if I look at what's changing, so if I change the data set, the only thing that's changing is the histogram, right? And so if I just sort of look at the difference in the score function, that difference is actually equal to the phi inner product of phi and P hat actually cancels. So that, or sorry, this P hat is like PT, whichever candidate thing the analyst has handed me just now. Okay, so if I take the difference of these two score functions, what I get is what's left over is phi times H of X minus H of Y. And actually notice that this is just the difference of phi I on the one entry of X that is different, that is in X but not in Y. So I'll call that X old. And the one entry of Y that is in Y but not in X. So I'll call that X new. Okay, so here I'm X and Y are data sets. They differ in one record, which I'm calling the record X old gets replaced with X new. And so if I just, this difference is at most 1. It's, sorry, 1 over, sorry, the difference is 1 over n times this. Oops. And so these are each numbers between 0 and 1, so their difference is somewhere between -1 and 1. Okay, so in particular, the absolute value of the change is at most 1 over n. So the sensitivity is really 1 over n. And so as long as we sample with the right distribution, actually, I guess we want to sample with this over 2, then we get something that's epsilon not differentially private. Okay, so what have we shown so far? What we've shown is that we've explained what the DP interface is doing. So there's this kind of, think of this thing as sort of protecting the data from the rest of the algorithm. And then there's the internal logic of the analyst. That is all like sort of outside of the privacy barrier. So we don't have to worry about privacy there. Okay, because in some sense, we're going to have this sort of like barrier that like really private data is only being processed to the left of the red line. All right, so what's the analyst going to do? The analyst is like in its head, it's trying to come up with distributions. And so what it will be doing is actually it'll be running a copy of the multiplicative weights algorithm. And so that will give it like some initial P1. And then what we're going to do is put it in a different color. So that will give us P1. Now we get back an index I1, and so we need to feed the multiplicative weights algorithm a cost vector, and the cost vector we're going to feed it is exactly like the query identified by the exponential mechanism. The multiplicative weights algorithm will do an update. It'll produce P2. And again, I will feed P2 to the interface and get back some I2. And so my second cost vector is going to be phi of I2. And so on and so on and so forth. And so like at the end, multiplicative weights produces P sub t. And what I hand it back is phi of I sub t. And then what I produce as my final output is just the average over all time steps of these things. So this is my p hat. Okay. And you might see a connection with the way we sort of averaged at the end of gradient descent when we talked about the gradient descent algorithm. And indeed, there is a connection. There is some similar thing going on. We'll see that when we need it. All right. But for now, I just want us to understand the structure of the algorithm. So again, there's something a little, actually, I think kind of cool going on, which is that we're using this online algorithm internally, not against an adversary, but really against ourselves. And the reason we're doing that is because we have very limited access. We want to use very limited access to the data. And so the only thing we're going to get back from the only thing we're going to kind of try to find out from the data at each step is, give me one query that like, one respect in which the synthetic data distribution I have does not look like the real data. And what the analyst will try to do is to try and improve its estimate. And that's exactly what we're going to analyze that process, but that's what's going on. Okay, so this is sort of the description. Let me just write out pseudocode for this algorithm, and then we'll talk about why this is a reasonable thing to do. All right. So here's our pseudocode. So this is the multiplicative weights via the exponential mechanism algorithm. It takes as input a data set X, a set of queries, parameters epsilon and delta. And it's got some internal parameters that we'll sort of figure out as we go. But anyway, the basic idea, it sets P1 to be the all ones vector. So it's a vector of length m. And then for t equals 1 to t to big T, we're going to say like I sub it is going to be what we get by running m naught on x and epsilon naught and p sub t. So m naught is this instance of the exponential mechanism. Then we set our cost vector to be the query corresponding to the output of m naught. And then we update PT using the multiplicative weights update. So I'll just call that like MW update, which updates the cost and has some parameter eta. And we're gonna just set eta just as we did in the multiplicative weights algorithm. We're gonna set that to log of m over t to get the regret bound we need. Okay, so this is just doing the same update we did when we talked about multiplicative weights last time. Okay, so we're roughly setting PT plus 1 to select a data record with probability exponentially high in the exponentially small in the cost it has experienced so far. And then finally we return the average. Okay, and actually, if you're paying attention closely, you'll notice that there's like, we're doing one more execution of the exponential mechanism than we really need, because P sub capital T plus 1 is never used. And don't worry about it. We're not gonna, we're not gonna optimize for that, although we could. All right. So this is our basic structure. The algorithm, the whole algorithm M is this whole blue or MWEM is the whole blue box. Okay, but the only place the data is being used is in these little executions of the exponential mechanism. All right. So the question, I think you should be asking, I hope you're asking, is like, why is this even remotely reasonable? Why is this not crazy? Okay. And let me see if I can explain a little bit, but basically that, the idea is at each stage, P sub t gets like closer in some sense that sort of try to explain closer to the true distribution, at least as measured by these queries. And there is we're not going to actually kind of prove it this way. We're going to use the, so the way we're going to analyze it is we're going to use the multiplicative weights guarantee as a black box. But indeed, if you sort of crack open the box and really try to understand what's going on inside, you'll see that this probability distribution P sub t, it's getting closer and closer in some measure of divergence to the true distribution. And that measure of divergence is called KL divergence. Okay, so since I know some of you have seen that notion, I'll say that. So we can show that what is called the Kullback-Leibler divergence between H and P decreases over the course of the algorithm. So we're not gonna do that really directly, but like that is what's going on. Okay, and if you don't know what KL divergence is, don't worry about it. We don't need it for the lecture. All right, so let's take a break and then we'll come back and sort of work through an example.